Alrighty, guys, welcome to Functions. This is day one for IM1, Intro to Functions. Feel free to look through the warm-up there. We're talking about the relationship between two quantities. Now, you can think about the relationship between two quantities as, well, there's a direct relationship, there's somewhat of a relationship, there's no relationship. That's when we kind of start talking about regression and stats. But here, we're talking about things that do have a relationship between each other. So obviously, when you're looking at the number of movie tickets that you purchase and the total cost, the more movie tickets that you purchase is going to have a direct effect on the total cost, right? So as you purchase more tickets, the total cost will increase. So what we say here is the total cost depends on the number of movie tickets purchased. So as you can see, it says circle the independent quantity, underline the dependent quantity. Let's look at another one here. We're talking about the number of students in attendance at school and the number of lunches served. So the number of lunches served is going to depend on the number of students that are at West Park High School, right? So when we're talking about two different variables, one will depend and be directly affected by a change of the other. Now, when that first one changes, so in this case, the number of students in attendance at West Park, the number of lunches served will increase as well. So we call the number of lunches served the dependent variable. Now, let's jump down to what we're talking about today. Make sure that you read through these learning goals. Very important. We're going to talk about function notation today. And just simply function notation is kind of tossing out this a sub n is equal to. And from now on, we're going to start using f as a function of x, okay? And if you were to mathematically say this, it's not f times x or fx. It is f as a function of x. Okay, and we'll talk more about what that means. So always important to read through those learning goals to make sure that you're aware of kind of what's coming. We also have our vocabulary there. There are quite a bit of new vocabulary terms. What we did in class here is we made sure that this was emphasized. This page is huge. Put stars around it. Said put smiley faces around it. Do whatever you have to do to make yourself aware that this page right here is very, very important. Okay, this page is very important because this is the 6 ways that we are going to represent a function. Some of them you've seen before. I guarantee you've seen ordered pairs. We've all seen some form of an equation. We've all seen some form of a graph and a table. These two right here, verbal and mapping, these may be somewhat new to you, but they're all ways that we can determine if something is a function or not. Okay? So graphically, when we determine if something is a function, what we did in class is we determined that, and you might need to do a little research here, but if you throw into Google, how can you determine, okay, this would be something that you definitely want to do in class. How can you determine if a graph is a function or not? Okay, and if you look that up, you would find something called the vertical line test. Now, you're going to want to do a little research on the vertical line test, but what the vertical line test basically says is if you run a vertical line from left to right, you could use like your pencil right now on the screen. If at any point your pencil touches 2 points on that graph, the graph being like the red line or the circle, whatever the function is, or the non-function, if it touches 2 points at any point, then it's not a function. So if you run it along A, well, it never touches 2 points, so it is a function. B, also a function. But with C, when you get to that vertical line there, when your pencil hits that vertical line, it is touching infinitely many points. So for each of these guys that are functions that you say yes to, yes, for example, on part A, because it passes the vertical line test. You'd also want to say also for each input, there is exactly one output. So for example, if you look at this guy right here, right? When you're running your pencil along from left to right and you hit that line, well, that line right there is touching at infinitely many points. So this input value x, where the line is crossing the x-axis, that has infinitely many outputs along that line, the outputs being the y values. So in order for something to be a function, it has to have one output for each input. E would not be a function F would not be a function, G would be a function, H would not be a function, and all for those same reasons, okay? Now for number 2, we created a sequence in class, okay? So for example, if we had the sequence, let's just go with 6, and we are gonna add, 5 each time. So 11, 16, 21, 26 would be our first 5 terms. What I asked everybody in class to do was then go back up and look at this third page here that we emphasize the importance of. And with that sequence, try to do the following. And that will definitely be something that you'll be assessed on coming up here soon. So I would encourage you to pause the video, and I'm going to pause it as well. And I'm going to work through these examples and then unpause and see if your solutions match mine. All right, so hopefully yours look similar. My ordered pairs are as follow because 6 is my first term, 11 is my second term, 16 is my third term, etc. Your equations here are an explicit arithmetic, a sub n is equal to the first term 6 plus the common difference 5 times n minus 1. Or this right here is in slope-intercept form. And we're going to emphasize this more in the day 2 notes, but the common difference, this 5 here, is actually your slope in slope-intercept form. And this 1 right here is actually your 0th term. So if you were to work backwards here, if you wanted to go to the left, then your 0th term would actually be 1, and you would get that by subtracting 5. So we'll talk about that more in the next notes. The verbal I made up, just something that makes sense as far as, something you might see in the real world. So on day 1, I have $6, and I add $5 to my account each day. Now, as far as mapping goes, this is just another way to show if something is a function or not. Now, if we had, for example, on day 1, I had $6. But on day 1, I also had $21. That doesn't make sense. That would show 2 outputs, 6 and 21, for the one input, 1, and that would just not be a function. So when we're looking at mapping, you need to have one input connecting to a single output. Now, the graph here is as follows. I just put in my ordered pairs here in the table. This is the equation here in slope-intercept form, and it goes through the points there on the graph, so everything checks out. So how are the graphs from example 1 different from the graph of your sequence? Well, there are many different things here, right? The graph of our sequence, it has a positive slope, just like A does, right? But you could say that it is different from B because B has a horizontal slope or 0 slope. You could say it's different from C because C and E and F and H are not functions, but my graph is a function. Something along those lines would work. Okay, now down here, this is just something that you can kind of read through on your own. Okay, but what this is saying is we have f of x is equal to 8x plus 15. This is just a different way to represent a function. It's called function notation. Now, when you have f and in parentheses x, once again, what this means here is, the way you say this is f as a function of x is equal to 8x plus 15. Now, when we consider the US Schurz function, C of S, now think about what could C of S mean? You'd want to go up and read the story here up above, and hopefully you see that C of S actually means, we're talking about the cost as a function of the number of shirts produced, okay? So the more shirts we produce, the more costly it's going to become. So there's a direct relationship there. Domain and range, we touched on a little bit. The domain is just the x values, okay? So the x values here. So the x values would just be the number of shirts that you produce. Now think about it. What's the lowest number of shirts that you could produce? Well, the lowest number of shirts that you could produce would be 0, obviously. What is the maximum number of shirts you can produce? Well, there is no max, right? I mean, it would just keep going on, so we're just going to call that infinity, okay? So the domain of our function would be 0 to infinity. Now the range, these are the y values, okay? Now if we're talking about the y values here, as we produce more shirts x, what's going to change? The cost, okay? So what's our lowest cost when we produce 0 shirts? Careful here, but the lowest cost that we produce when we produce 0 shirts would be 15, right? And then our cost is going to continue to increase infinitely as we produce more shirts, okay? So our range here is going to be from 15 to infinity. Describe the possible domain and range for this situation. I should have read this a little bit more careful. In this particular situation, these would be the solutions. Okay. But technically, if you were to graph this thing, y is equal to 8x plus 15 on Desmos, it's going to look a lot like what we just did on Desmos. And let me actually throw it in a Desmos right here, 8x plus 15. You can see that this thing continues infinitely in either direction from left to right, and it goes infinitely in either direction up and down. So actually what we would say here is that the domain of the function is all real numbers. There is no number for x that our function does not touch. And for our range, all real numbers, because once again, there is no number on our y value that our function does not touch. Okay, so now at this point, what you guys are going to want to do is you want to go through the self-assessment and watch the video afterwards, and then go and give that portfolio a try. All righty, guys, good job.